Our prominent speakers are actually coming from a variety of angles in the field of communication, and we'll discuss all types of use cases in AI, deep learning, machine learning, in the different layers of communication and cyber. I'm sure that we all can gain from their practical experience and also learn and discover more angles and more subjects under the area of communication, which is not so much explored. And we're going to hear about 4 angles from our speaker. The first one will take the angle of the deep learning in the signal analytics, challenges and use cases. Another angle would be from the area of the cybersecurity, which is the highest level of communication, from the defensive side, and also from AI on the adversarial and the offensive side, and how to challenge those risks. The third lecture would be of IP level of IP hijacking and ways to detect them using deep learning over BGP protocols. And the fourth session, the fourth lecture would be about using the data in 5G mobile networks, how to improve latency, how to balance the trade-off between the latency and the accuracy, and how to use machine learning altogether. So I'm sure it's going to be a very interesting session, and we're going to cover 360 of communication and cyber matters and subjects using AI, deep learning, machine learning. Our first our first speaker is Mr. Ziv Freund from Elistra. He's the head of the AI R&D group in Elistra and Elbit Systems. Ziv joined the Elbit system in 2002, and since then he was leading algorithm engineering. He managed Elistra computer vision R&D group and designed algorithms for Elistra's IR-based missile warning systems. Since 2017, he has been leading of the AI R&D group at Elistra, holds master's degree in electrical engineering and business administration from Tel Aviv University. Ziv, the stage is yours. Good luck.
Okay, so thank you very much for the introduction, and I'm really happy to present here again in the AI Week. So let me start by introducing Elbit. So I'm coming from Elbit Systems, EW and SIGINT Elistra, which is a division of Elbit. Elbit Systems is the largest defense company in Israel, and Elistra is one of its divisions. We are located in Holon. And our main business is electronic signals, and more specifically, providing intelligence on electronic signals. So let's start by understanding what do I mean by electronic signals. So there are many types of signal in the universe. Most of them are natural signals like sound waves or radiation. But we're concentrated on signals that are generated by engineers. So they are pretty much the opposite of natural signals. And we're interested in providing intelligence for those signals. So if we take a look at the electromagnetic spectrum, so we are interested in the areas starting from tens or hundreds of megahertz, where we can find radio stations, and we go up to hundreds of gigahertz, even terahertz, where we can find radars of different types. And if we want to divide the arena according to the usage, so we usually divide it into communication signals, what we call common communication intelligence, where we handle every type of communication signal, starting from mobile phones to airborne communication. And all the other signals, they are simply called electronic signals, or ELINT. And there you can find all types of radar, from weather condition radars to collision avoidance radars, and other signals such as GPS signals. So what are we trying to do with the signals? What are the applications that we are addressing? So first of all, we want to detect all of these signals in the electromagnetic spectrum. Once we have detected them, we want to classify them to understand what type of signals we're facing or dealing. And then we would also like to geolocate the signals to know their location, the location of the transmission of the signal. So these are all low-level applications that provide us with entities in the communication arena. Once we've done collecting these entities, we can go to the higher levels where we can look for relations between the different entities. We can look for misuse or anomalies. And if we find threats or hostile communication emitters, we can try to counter them, to stop them from doing their harm. So where does AI come into play? How do we use AI in this field? So I think I will start with a dive into a single block of this many applications. The first block, which is, well, always a good place to start. And this is the detection. So let's speak about detection of electronic signals. So what are we dealing with? Well, we have an antenna. The antenna collects the signals. We have a receiver in radio frequency receiver that does some amplification, amplifies the signal, maybe filters the signal. And then we digitize the signal using analog to digital converter and sampling. And then we have a digital signal, digital actually bandwidth. Maybe there are many signals over there, and we want to detect the signal and to measure its parameters. So this might look like an easy task, right? Because all you need to do is to estimate the noise of the receiver or the channel, and then to put some threshold according to the false alarms that you are able to sustain, and then just detect everything that goes above that threshold. Well, that's true if you have only one emitter, but if you have many transmitters, then of course this is not the case. And you all understand that when you think about the communication arena, there are many emitters. So of course, this will not work in the time domain, but we all took our bachelor's degree in engineering. We all know Fourier transform, and we all know that engineers like to modulate the transmissions in the frequency domain by multiplying them with the sine or cosine. And then we can use the Fourier transform, the well-known Fourier transform, in order to detect these signals. And if we want to combine both time and frequency, well, signal processing comes to the help again, to the rescue again, and we can do a time frequency representation using some kind of wavelet or a spectrogram that shows us both the frequency and the time of the signals. So far, no AI. So let's look again at the problem. This is a synthetic simulation of a communication arena. You can see different transmissions, and the black bounding boxes, they are the ground truth. And they are actually the output that we're trying to predict. Now, this might seem like still an easy problem. You might think that we don't even need AI. We can simply apply computer vision edge detection, then some kind of bounding box regression, and that's about it. And, if you really insist on AI, so, well, just use YOLO or some kind of other object detection algorithm from the internet, then fine tune it, and that's about it. 1 month of work and you're ready to deploy. Well, that's hardly the case. It took us many months of research, intensive research, before we could deploy our solution. And now I will guide you through the practical problems that you're facing when you're trying to adapt an algorithm to a different domain, in our case, the communication arena. So let's start with convincing you why computer vision is a very good solution. This is what we did before deep learning, but it can get you so far. So let's look at the example. On the left, you can see computer vision output. The green rectangles are the detections, And on the right, you can see our deep learning solution. So if you look at the transmission that I've selected, in this case, we have a communication signal that is that has a central bandwidth and has some side lobes. So it transmits also in actually like free bands. So the computer vision algorithm does not understand communication, detects all three signals as three separate detections. The deep learning algorithm, well, it understands communication. It knows that this is a single transmitter. And if you think this is, well, big deal, so you got three detections instead of one, no, this is a major issue if you're facing an arena with thousands of transmitters. But this is not the main problem. The main problem is SNR. And SNR is, sometimes neglected when you're using, when you think about computer vision, you hardly think about SNR. But in a communication arena, in a SIGINT arena, this is the main thing. This is what we're looking for. We're looking to detect signals in very low signal to noise ratios. And when you go to low signal to noise ratio, computer vision algorithms simply break down because they do not see the entire picture. Whatever edge detection algorithm you might do, you will get images similar to the one you see on the left. And then you will have to try to build some rule-based logic in order to combine them. It will simply not work. And deep learning, well, you can see the results. It sees the entire picture and is able to detect in very low SNRs. We have done a lot of architectural changes or development research in order to improve this to detecting low SNRs. So this was a lot of work that we had to do. So maybe I've convinced you about the computer vision, but what about YOLO? So let's just download YOLO, fine-tune it, and that's about it. So why not? Well, the reason is that there is a basic difference between computer vision object detection and communication arena bounding box detection. And the difference is that the main problem, as you can see on the right, in a computer vision object detection is to learn the different distributions of backgrounds versus objects. And in a communication arena, this is not the problem. I mean, you can see for yourself, it's very easy to know where are the signals. So what is the problem in a communication arena? So they're different. First of all, the SNR, we already spoke about that, but this is just the beginning. In a communication arena, you have overlapping signals. This is your life. I mean, it's not just a little bit of overlapping. No, this happens all the time, and you have to address it. And then you have interferences in this, just minor interference that you see here. This is just, some example, but it can be hell. And you have to take this into account. You cannot just, train your networks in a sterile environment and hope that it will do well in real life. It doesn't happen. You have to address it. And this takes a lot of effort. And another difference is the requirements. But we don't really care, the accuracy of the bounding box. I mean, I don't really know where the dog starts if you have to put it inside a rectangle, but we really care about it in the communication arena. Think about missing a little bit of the time domain, a little bit of the frequency. That's catastrophic because you won't be able to reconstruct your signal if you're missing the beginning of it, for example. So this has made us do many changes in the loss function of the network. And there is another basic difference. When you think about computer vision object detection, you're facing real life natural images. So they have some constraints on their sizes. And I think all major deep learning algorithms are based on anchors, which have some assumption on the sizes and the allocation of the anchors. But in a SIGINT arena, there is no such limitation. Since it is built by engineers, there is no limitation. You can have one pixel transmissions. You can have very long transmissions, very wide transmissions, everything. So you really have a problem if you're trying, to use the anchors that are supplied in a traditional computer vision object detection algorithm. So what can we do? So first of all, there are some papers on this. You must use some kind of multi-resolution, but this is done also in YOLO, but this is not enough. This is just the beginning. You can do some signal pre-processing. You can select your anchors smartly. You can even do this adaptively. There are a few papers on that as well. And you can go back to the two-stage, the old, good old two-stage algorithm, but with a twist. I mean, because we cannot endure the very high computational cost of these algorithms. And in the end, a lot of good engineering to make this problem go away. And you can even consider going to other solutions that are not anchor-based solutions. So all of this is a lot of effort that you have to do in order to solve this problem. So this was just, an example of the detection problem, but this is just the first block. If you go further, so you have many detections, but you have to cluster them somehow. If you look at the frequency versus time, so each of these black points is a bounding box that we have detected. We have to cluster them into different transmitters in order to classify them. So of course, we use deep learning for this clustering, for these features. And then also for the classification step, we use deep learning again, because deep learning has great features. Before we used classical electronic-based features. Well, they had limitations, and also each time you have a new transmission, you have to invest a lot of energy in building new features or new classifiers. In deep learning, you don't have to do that. If you have enough data, you learn good features, and then you simply train one-shot learners or a few-shot learners, and you have a new classifier with very little effort. And last, if you go to the localization problem, so just a short explanation on how do we localize these signals. So if you have two antennas, you can measure and you can somehow correlate the time between the two antennas and measure the differences in the time of arrival. Then you can have an equation that is bounding the location of the emitter according to the difference in time, because they move in the speed of light and in a straight line. And if you have more than one antenna, you can actually solve these equations and find the accurate location of the transmitter. But once you have an urban scenario, you're starting to have multipaths, you have reflections, and then your estimation goes wrong. And again, we use AI in this very challenging scenario to significantly improve our estimation. And of course, this was just the low level. If you look at the insight level, well, there, of course, AI is the basic. I mean, this is where we go to. This is the go-to for learning relationships, for anomaly detection, for fusion, and other applications. So to summarize, so this was just an overview of some of the problems that we're facing and how deep learning actually changes our SIGINT systems. And we've taken a look in detection, but I think I've convinced you that there's a lot of work to do. But as Uri said earlier, this is pretty much terra incognita. So this is, in one way, it's great. It's really, really fun, because you have to do all the research from scratch. You have very little papers to rely on. But on the bad side, you don't know your path. You have to try many, many ways until you get the solution right. So this is a lot of work. This is really, really exciting. We're actually, doing research from the beginning, and it's very exciting. And naturally, if this is interesting to you, if you're AI expert or interested in signal processing, so feel free to contact me. And also, if you're from the academia and these problems sound challenging to you or interesting, So we will be really happy to collaborate. So thank you very much. And now if there are some questions, I'll be happy to answer.
Thank you, Ziv. Actually, I'm double excited because I tackled some of the challenges you mentioned through my service in A200, and well, we didn't have AI back those days. We had to do some other algorithms. Some of them are pretty much similar, but with a much less. I mean, the performances were much less promising than what you demonstrated. So it's all inspiring, and it's great to see it. I will try to take two questions from the audience and make them one. You were talking about using deep learning in signal communication. So it could be in signals, but also in radar. And I would like to take another question right from the audience about the use in autonomous vehicles for those methods, because it's a noisy environment. And from one side, and I'm not sure if you experienced some applications in that field, but taking other ways of transmitting and communication and trying to use deep learning, machine learning to improve the performances, but also in the case of detection and signal separation in the area of autonomous vehicles, So, but I think radar is the main question here.
Well, first of all, there is a big difference between communication signals and radars, because you go from tens of megahertz to hundreds of gigahertz, and this affects how the signals look, and you have to address it. You cannot use the same algorithms and the same architectures. And I think that regarding to autonomous vehicles, so there is a major difference between what we do, and this is the collaboration. We do not have collaboration from the other side. We do not know who is transmitting. We open a receiver and we try to detect whatever we can, like you did in your Army service. And in autonomous vehicles, I imagine it's not my field, but I imagine there can be some collaboration because you can speak with each other, you can introduce yourself. So I think this makes the problem a lot easier. Well, I can imagine that there are some overlapping or some same challenges, but I think that the fact that we're not collaborating makes this problem very much different.
Thank you. Another question from a different direction. You spoke about representing the signals as a spectrum. So can we train the network to learn from spectral representation from the FFT type of directly, and not like moving between
so that's a really good question, because there's a big cost when you go to the spectrogram. You pay for the representation. You represent the data as an image, although it came as a signal. And this is a lot of, and this causes the network to be very high computational. So we've done some attempts on this. I think this is one of the open issues. How can you, it's very easy to train an FFT, but it's not what you want. If you just train an FFT, you go back to the representation, so this doesn't help you much. So the goal is to combine both of these just by using 1D CNNs or other one-dimensional layers. So I think this is an open issue, and it could be really exciting to try to solve this.